it illustrates the principle that you are free to choose, but not free to choose your consequences. It is a foundational principle of life, and math class is part of life. So can't get around it. The semester is winding down. The end is coming soon. So the end is near. And for this class, we really have 3 big ideas to cover still. So before the end. So who'd like to start us off with a prayer? Anyone? Bueller? Thank you.
Our dear Heavenly Father, we're thankful that we're able to be here together in our calculus class today. We ask Thee to bless us, so we'll be able to understand the things which are being taught. Help us, so we'll be able to apply it in our schoolwork and hopefully in our future lives as well. Help us, so we'll be able to recognize the importance of what we're learning, and we say these things in the name of Jesus Christ. Amen.
Amen. Thank you. A few things. There was a miskeyed multiple choice problem on the midterm. They've re-scored it, and we will get the new scores up. They're not up yet. So it was problem number 2. There were 3 correct answers. It was the test for divergence. You were testing to see which ones you knew diverged by the test for divergence. And there was one that actually did, but it wasn't coded as being as it did. So it won't lower your score. It will only raise your score. So, okay. The final exam of the semester is actually, it will just be multiple choice. So we don't have time to get it graded. To do like one of the other midterms, we won't have time to get it graded and back to you before you have to take the final. So it will just be multiple choice. I know some of you like that and some of you don't like that. Yeah, the final will be like a midterm. It'll have short answer and free response and multiple choice problems. Okay. So take a couple minutes. You can work on that. That problem, if you finish that one, perform the ratio test. I can change what that is.
You should push add on the G to say knowing that you get 0 points.
Yes. Oh yeah, that should be K right here. So sorry, my bad. There. That is way harder. Sorry. I had the index as n, and I had the power as n, but then it uses a. They're supposed to all be k. A lot of you probably ignored that, which is could be good or could be bad. So. Our book uses n almost all the time. Some books use k almost all the time. So you see them both ways. So. Or I. I is a common index. Okay. So while you're working on that problem, there isn't a lot of new material in this section that you read for today, the strategy for testing series 11.7. It's really just a practice. Instead of working on one particular technique, now we should be able to throw any series at you, and you have to reason through how you're going to decide how you're going to test it, whether it converges or diverges, whether it's absolutely convergent or conditionally convergent. So, so we have a whole load of tests, of convergence tests that we can now use. And why don't we start making a list of those? So, test for divergence. So if the sequence of terms goes to 0, then we know it converges. Okay, so I just lied. No, that's not right. Okay, I know some of you were working on that problem, but no, if it does not go to 0, then it diverges. If the terms go to 0, what do we know? Absolutely nothing. So, test for divergence, geometric series test, telescoping series. Isn't really a test, but if you can find the finite sum, then you know it converges. Integral test, comparison test, limit, comparison test, alternating series test, root test, ratio test, p-test. Did I miss any? Yep, I'll show you I'll show you that test today. So there's one more that we'll get on that list. Okay. Snap if you need more time for this problem. Okay. Take one more minute. You bet. worries. Okay. All right, this is going off in 10 seconds. Make sure you chime in. And we'll go over this problem. Any more changes? All right. So here I'm setting up the ratio test. The limit is k goes to infinity. Oops. Minus 1 to the k. Here I have k factorial squared over 2k factorial. Okay. Let's invert and multiply in that denominator. We already know that with the absolute value we don't have to worry about the alternating part. So what do we end up with? This k plus 1 factorial squared I'm going to write as k plus 1 times k factorial times k plus 1 times k factorial. Okay. And then here I'll write this denominator as 2k plus 2 times 2k plus 1 times 2k factorial. And then I multiply that by this piece here is coming up. So 2k factorial over k factorial squared. And now we get a few nice things that cancel out. That divides out with that. The squared here divides out with those two. So what do we end up with? But the limit as k goes to infinity of k plus 1 quantity squared times 2k plus 2 and 2k plus 1. And what happens with that one? Yep, you can do L'Hopital's rule. You can rewrite this. K squared plus 2k plus 1 over 4k squared plus 6k plus 1, 2, plus 2. So now you can divide by the highest power of k, and then you'll get 1/4, or you can do L'Hopital's rule twice, and you get 1/4. So either one of those, you get 1/4. So what does that mean? It's absolutely convergent. If we set up that limit and it's less than 1, then we know it converges. Absolutely. Yes. Let's skip which step. Oh, you should show why you know this is 1/4. If you say, hey, the leading term is k squared here, the leading term is 4k squared here, and then where do you go from there? Yeah, then you can do L'Hopital's rule with the leading term, or you can divide by k squared. Yeah. I would err on the side of writing things down, and don't give the graders an excuse to pick up. Yeah, so like right here. So that k plus 1 factorial squared, that's the same as k plus 1 factorial times k plus 1 factorial. So then I just thought of it that way, and then I just wrote them out separately. So does that help? Okay. All right, any other questions? Okay. All right. I did say last time we would finish this problem. Remember, we had this one written in a weird way. We keep having this product and adding this product as we add more terms. We found the general term, and then we applied L'Hopital, the ratio test to this one. But we hadn't simplified or finished this. So the limit as n goes to infinity. All of this will cancel out with all of that. That'll divide to be 1. So then in the numerator you end up with 3n plus 3 minus 1, and then in the denominator you end up with 2n plus 2 plus 1. And so here you get 3n plus 4, and here you get, oh, thanks, 2n plus 3. Then you do L'Hopital's rule once, because you get infinity over infinity, you get a 3/2. So we know it diverges. Okay? So with the ratio test, the limit we got was larger than 1, so we know it diverges. Okay? Okay, I'm going to teach you one more test. This is called the Cauchy Condensation Test. So Cauchy, that's Cauchy. It's the last name of a very famous mathematician. I think he was French. So Cauchy Condensation Test. This is to test series. So the Cauchy Condensation Test says if you have some series, it converges if and only if 2 to the n times f of 2 to the n converges. Oops, I forgot to put converges in there. That means if this new series over here, if it converges, the original series converges. If it diverges, the original series diverges. And you're wondering why we would need this, because basically we're going to turn the series into a new form, and then we're going to apply our test to that series. And this makes some things really slick. So what this says is everywhere there is, we have to multiply by 2 to the n, and then everywhere there's an n, we replace with 2 to the n. So here we'll take harmonic series. We already know it diverges by the p-test, but it's kind of on the cusp, right? I mean, like, if you raise that power just a little bit, then it will diverge. But what happens when we apply the Cauchy condensation test? We're going to get a new series. I'm going to multiply by 2 to the n, and everywhere there's an n, I replace with 2 to the n. So you end up with that series. It diverges, right? Test for divergence, the terms don't even go to 0. Okay? So it makes it so terms that are going to convert, like series that converge, they converge quickly. In terms of series that diverge, they diverge quickly. So the place that's really handy is when you have natural logs. Usually what we have to do to handle natural logs is, that's a clue that you're going to have to use the integral test. But if you've got natural logs, try the Cauchy condensation test. So we've done this problem before. 1 over n times the natural log of n. Why don't you guys try the Cauchy condensation test on this and see what you get? Okay. Okay, so I did my work up here. So I multiplied by 2 to the n, and then everywhere there was an n, I replaced with 2 to the n, and these 2 to the n's divide out, and then I used log rules to pull that n out front. So you get n natural log of 2. Well, natural log of 2 is just a constant, so I pulled out the 1 over the natural log of 2, and I end up with the summation of 1 over n. There's the harmonic series diverged by the p-test. Just a bit simpler than trying to do integration, the integral test. So this does only work. I need to tell you when this does work. It needs to be positive and decreasing. Okay? So it doesn't test for if you've got things that are going up and down, or if you've got can't think of the word. Anyway, technically it's non-negative and non-increasing, but so there's a difference between decreasing and non-increasing, because you can't have terms that stay the same. That's not decreasing, but it's not increasing. Yes? Yep, absolutely. I didn't mean that as a joke, as a pun. So, all right, so let's add that to our list. Here we've got a bunch, and we've got one more here. So the Cauchy condensation test. So if you use the Cauchy condensation test, make sure you write it down. Well, I guess if it's multiple choice, probably you don't have to, but on the final exam, if you're using it, say, I'm using the Cauchy condensation test, I get this is the new series, and then you test that, so you can say, like, by the p-test, this converges, so by the Cauchy condensation test, my original one converges. So that's how that works. Okay. Quickly, this should be like your number one option. Take a look, see if you can tell if it's not going to 0. Right? When you see a series, if it's not going to 0, you have an easy way to show that. Boom. Do test for divergence. If you have the geometric series test and the p-test, they have nice forms. If it's in the forms of those, then look to do that. If you have something that's close to those, then do the comparison test or the limit comparison test. Okay, we usually end up doing a p-test or a geometric series test on the comparison or limit comparison test. What's a clue for telescoping series? Yeah, you have a term minus another term, or you have something that looks like partial fractions. Okay, something you could apply partial fractions to. Integral test. Natural logs are a big key there if you have the natural log of n. Not always. There are other times when you could do that. It usually ends up being kind of the last thing people try. Alternating series. Big clue is if you've got a minus 1 to the n or something like that, or cosine of n pi, things like that. And root test and ratio test. If you've got factorials or lots of nth powers, then the ratio test. Root test, you've got nth powers. And the Cauchy condensation, the natural log is another is another clue that might be helpful. Okay. There are online, if you Google series test flow charts, it'll have these flow charts to say, first look for this, and then look for this, and if you do that, come over here and try this test. I find them more confusing than helpful, but if they're helpful for you, then search and use them. But if you feel like you're dependent on those before you go into an exam, then you do not know the material well enough. So it's a good test that way. Okay, let me give you some. I'm going to write down 4 or 5 here for you guys to work on. you already know how to do one, don't spend time doing it. Work on the ones that you might have trouble with. Oh, did I? So, in Samoan, they actually have two different ways of speaking where they'll replace their T's with K's and then their N's with NG's. So you can that's what I'm doing. You just switch back and forth. You can say, yeah, kanata or kangaka. It means the same thing. Tangata or kanata. But all right. So I picked this one. This is one of the harder ones to start with. So this is one you can actually do by test for divergence. It just takes a little bit of work to find what that limit is as k goes to infinity. And maybe it's not obvious that it might not be obvious. It wasn't obvious to me, but one of my students in the last class tried it and was able to figure it out. So you can just start doing L'Hopital's rule because you get an infinity over infinity, and each time you do that, you do have to do the chain rule where the derivative of the natural log of k becomes the 1 over k, but since that 1 over k is in the denominator, you end up multiplying by k in the numerator again, and then you can do it again and again, and you keep lowering the value of this exponent right here. And eventually you just get to k over 120, and that diverges, goes to infinity. So that's one option. You can do the Cauchy condensation test, and so you replace k here with 2 to the k. That is supposed to be a k up there in that exponent. You replace the k here with 2 to the k, and you have to multiply by 2 to the k. And then you do some simplification, and you end up with this. So here you have an exponential over a polynomial. So the exponentials will grow faster. You can show that with the limit comparison test with 4 to the k, which is probably easiest. Or you can do L'Hopital's rule 5 times. And you'll get 4 to the k over, 4 to the k times the natural log of 4 a few times over 120. So, yes? Let me write down, make sure I caught what you said. So k over the natural log of k, and k over the natural log of k to the 5th, which is what we have, right? Yeah. So this one is smaller once k is large enough, right? But this one diverges, right? But it's larger. Your sign's on the wrong side. Yeah. But that's the kind of thing you want to be looking at, right? It's exactly the kind of thinking you want to be doing. It's like, hey, can I find something that's similar that I can handle easier and do a comparison test? It's great that you're thinking about things like that. But in this case, it doesn't work. Okay? Did someone else have another way to do this? You can actually try it by the integral test. It's not nice in this form, but it would be really nice if we had an x in the denominator. Well, if you multiply the numerator and the denominator by x, then you can do a u sub with u equals the natural log of x. And you still get something that you can't integrate or integrate very easily, but it's easy to see that it doesn't even go to 0. It goes to infinity, so you know the integral to infinity is going to be infinite. So you can just do it with the comparison test. So another option. All right. Let's go back. What else did we have here? Which one do you want to see next? Oh yeah, let's do the tangent one. If you haven't done the tangent one yet, take just 30 seconds to start thinking about the tangent one. Okay? I'll put a hint up here. So keep your heads down if you don't want the hint. All right. How did we handle the sine of 1 over n? Flip back in your books, in your notes from section probably 11.3, comparison, limit comparison test. How did we handle sine of 1 over n? We did compare it. We did comparison tests, and what did we compare it with? Not x. 1 over n. So we did a limit comparison test. As n goes to infinity of sine of 1 over n. 1 over n. So we are looking at the sine of the. We're comparing it to the input. So this is the. This is the famous limit that you learn in Calc 1. That equals 1. This is similar. You still have the sine of something going to 0 compared to that thing going to 0. So, and you can use the same strategy here. You can do the limit comparison test with 1 over n. So the limit as n goes to infinity. Tangent of 1 over n over 1 over n. Okay, take a minute and see if you can, where would you go from there on that problem? See if you and your neighbors can solve that. What options do we have here? We're trying to figure out this limit. What should we be thinking? We have a 0 over a 0 form, so you can think L'Hopital's. Nice. So you can take the derivative of the numerator. Derivative of secant is, derivative of tangent is secant squared times the derivative of 1 over n using the chain rule. In the denominator, we have to take the derivative of 1 over n. I'm going to be lazy and not actually take those because they're just going to cancel each other out. And what's the limit as n goes to infinity of this? Well, that just goes to secant squared of 0. What's secant of 0? Secant's 1 over cosine. What's cosine of 0? 1. So secant 1 over 1 is is 1, so 1 squared is 1, so that goes to 1. So what does that tell us? Yep, they do the same. And 1 over n diverges by the p-test. So tangent of 1 over n diverges by the limit comparison test. Okay, there's another way to do this problem. If you know this is equal to 1 already, this limit over here, then you can just rewrite tangent as sine over cosine. So you get the limit as of sine of 1 over n over cosine of 1 over n times 1 over 1 over n. And then this much, that goes to 1. And then you get just, in the denominator, you get cosine of 0, which is 1. 1 over 1. So that's another way you don't have to do the derivatives there. Okay. What's the next problem you guys want to do? Maybe we can just talk about some of these really fast. What about this problem? So you first should recognize what about this series? It's an alternating series. Okay? So for this alternating series, is it absolutely convergent, or is it conditionally convergent, or is it divergent? It's conditionally convergent. The absolute value of that is going to be 1 over k minus 1. And that will diverge by, you just have to compare to, yeah. So compared to the harmonic series, that diverges. So it doesn't absolutely converge, but with those alternating signs in there, does it converge? Yeah, we can do the alternating series test. Are the terms going to 0? Yep, the terms go to 0. Is each one smaller than the one before it? Yep, because as k grows, as k grows, the denominator gets larger, so the whole thing gets smaller. So it converges conditionally. By the alternating series test. Okay. What about this one? I should number these. What about number 2 here? Okay. We can say it's absolutely convergent. There's not a big difference here of saying it's absolutely or just convergent, because there's only one. We don't have to worry about conditional here because there's no negative signs. What are some options? What are some tests we could use in this one? Ratio test works really nice here. Anything else? You can do the roots test too. It's a little bit trickier. Denominator's good, but yeah. Is there a nice comparison here? You can do limit comparison with just 1 over 5n. So limit comparison test to the sum of 1 over 5n. That's nice. Wait, is that right? No. Sorry, n squared over 5n. You can do limit comparison test with this. And this one is really nice with the root test, because you get the nth root of n squared, which goes to 1. And you get the nth root of 5 to the n, which goes to 5. So you just end up with 1/5. So by the root test here. And so then you can do limit comparison test with that. It's probably more work that way than the ratio test. Okay, what about this one? The integral test. Oh, yeah, integral test is nice. You do a u sub with u equals 1 over x? Yeah. Oh, very nice. How else could you do this one? You could try the ratio test with what? I mean, you could try the ratio test. I think that you could just get 1, I think, if you try the ratio test, don't you? I don't think the ratio test for root test will work here because you'll just get inconclusive. You can do a limit comparison test with 1 over n squared. Because e to the 1 over n, as n goes to infinity, that's going to go to 1, so you're going to get close to 1 over n squared. You know that converges, so you can do a limit comparison test with that, and that also works. And what strategy do you do with this one? Ratio test. It's a bit of a bear, but it works. And it diverges. Have a great day.